In section 1.1, Introduction to Graphing, we kind of start over from early algebra days that most of you should probably have seen and had, about how we graph, basically, and then we move into more specific and direct techniques as far as graphing lines and graphing other things as we move along with this. So when it's asking you here to graph the following, y equals 2x plus 1. Now, if you remember this being in slope-intercept form, and remember the rules for doing that, by all means, go ahead, do it. But essentially, what this is asking you to do is, if you don't remember it, to go back to some of your basics in algebra and say, okay, well, I have these x values here that I'm looking to figure out what they are right here. And so what I would do to find the y values, so for -2, for instance, I would do 2 times -2 plus 1, which is -4 plus 1, which is -3, and get the y coordinate. And do the same thing for -1, -2 plus 1 is -1, and you would continue doing that down the line until you get all the values that you need. And from this information here, then I have enough information now to plot these points. So -2, -3 would be here. -1, -1 would be here. 0, 1 would be here. 1, 3 would be here. And 2, 5 would be here. And I can see the pattern develop there. And I'm just going to basically make that pattern this straight line. Now we have other ways of graphing lines, and we're going to go through those in this particular lesson, or later as we walk through this unit. But so now in instances like this, you could leave the equation as it is because we have the x values, and I could do some algebra to solve for y. So for instance, if I just take the -8, which gives me -24 plus 4y equals 12. I would add 24 to both sides, and I would divide both sides by 4 to get 9. So -8, 9 would be a point. I also had the option, I could do something very similar and, solve this equation for y, since the y's are what I'm looking for, and then dividing both sides by 4 completely. Remembering to distribute that division, I would have -3 fourths x plus 3. And then I can plug the numbers into this formula. So if I do like the -4, for instance, maybe use a different color for this, which would give me 3 plus 3, which equals 6. And I would, keep seeing the pattern here, or, keep plugging in these numbers. That's what they would end up being, and so that's what I would plot. And that would be the pattern right there. So you could see, you could do basic graphing just by plotting points along the line. Now, that gets to be tricky as you get to more complicated functions, and there certainly are shortcuts, especially for linear functions, that you learned along the way. So, but your calculator could also assist you as well, because if you have your calculator, you can then, get an idea what it looks like, and then maybe focus on certain areas. So let's see how the calculator could do it. And so for this, I'm just going to pull up a virtual version of the calculator for our purposes for this. And maybe shrink it a little bit. There we go. Okay. Graphing these on a TI calculator is pretty straightforward. Now this is kind of emulating a newer version. It may have colors and things like that. Yours may not. So, as long as you're getting the same graph, that's fine too. So a few features on the calculator that can assist you with this, just to kind of show you. I'm going to just put in the formula for this. So I'm going to have x squared plus 3x minus 10. And now I have that formula written in here. Now I might want to set my window up so that I can see this really well. And oftentimes if you're given a graphing region, take for granted the fact that, if I'm giving you a graphing region, it's probably a good enough graphing region to see what's going on there. So that's what, you should kind of set it at. And it looks like, my x's go from a -10, which isn't listed here, but I can see -9, -10 to 10. So for my x's, I'm going to go from -10 to 10, which is usually the standard. It's already there. And my y's, it looks like I'm going from a -15 up to 10. So I'm going to say -15 here, here, and here. When you see these XCL commands, that tells you like how you're going up. So these are going by 1. So my scaling for each one of these is 1. The resolution, these other things, I would say, you don't necessarily have to mess with. It kind of helps you if you're trying to do a trace and things like that to be more specific. But there's better ways to come up with points, and eventually we'll show you. So now, if I hit the graph for this, I can see what the graph looks like. And the thing is, though, whenever you're asked for a graph, and even though the calculator does give you a graph, we're still looking for you to be somewhat precise with this, so um, so I don't want, and no one wants to see you just basically just like put like, just come in here and say, okay, I'm just going to, you know, it'll kind of look like this. So I'm just going to put in just a thing like that and expect to get points for it, because you can see, even when I just basically do that really quick, it's, kind of the shape, but, it's off a little bit, so, um, you have the right idea, but it's not what we're looking for. So, one of the things that your calculator can do, if you look up here above the graph, there's a table command. So I can hit second and table, and this gives me some ordered pairs that, make up the points here. So I could go to some of these things, maybe say, okay, -7, 18 would be kind of hard to draw, but I could draw -6, 8. I could draw -5, 0. And I could certainly be a little bit more precise with what's there. -4, -6, and so forth and so on as I go through these. So, I mean, you can see it's an ugly looking graph that I drew here, but at least I have some points that I marked that show it's a little bit more precise than the one I drew that looked a little nicer and, was off by discrepancies. So, make sure that you are, graphing more accurately than, making it look perfect. Now, another question you'll often be asked to do is to determine whether or not the ordered pairs you're given, especially since a lot of these equations are going to have two variables, x's and y's, whether or not they're solutions or not. And again, that's a pretty easy process if you know what to look for. You have to remember that your ordered pairs, or any coordinates, are just combinations of x's and y's. And what you're looking to do is see, okay, well, which if any of these makes this equation here true. So if I take the first point, 2, -2, y is -2. A little question mark here because I don't know yet. 3/2, 2 minus 5. It's 3/2 times 2 is 3. Minus 5, which does equal -2. So does -2 equal -2? Check. So this one is definitely a solution. Whereas if I do -4, 10, So that's not true. So negative 410 is not a solution. And lastly, for 6, 4, so 6, 4 would be a solution as well. Which one of these, could be more than one, are solutions to the equation a squared plus b squared equals 25. Much like the previous one, I'm just going to do substitutions for each one of these, and I'm going to go to a different color to keep these all straight. So I worked out these problems to the point where I can answer some of these questions now. In the first one, I ended up with negative 0 squared, which is, of course, nothing, so I don't really have to consider this anymore. Is negative 5 squared 25? Well, negative 5 times negative 5 is 25, so this indeed is a solution. When I square negative square root 10, I get 10. When I square negative square root of 15, I get 15. Is 10 plus 15 25? Sure is. So that's a solution. When I use 2 and negative 4 for a and b, I get 2 squared plus negative 4 squared, which is 4 plus 16. Is that equal 25? No. And just so you know, I kind of took for granted here for this. Most of the time we're used to dealing with x's and y's. This one was dealing with a's and b's. And much like x's and y's, anytime you're given an ordered pair, you assume alphabetical order unless told otherwise. So, each one of these was an A followed by a B. So keep that in mind as well as you go through these. And so that's how you determine if you have solutions represented as ordered pairs. Now let's get into using something known as the distance formula. Now you will often be asked to find the distance between 2 points in a coordinate system. There's two cases that make it really easy. The first easy case is when you have a horizontal line, like this one. And I mean, basically here, all I really have to be able to do, it's just like a number line, is count. I could say, well, I'll go from negative 4 to 2. That's 1, 2, 3, 4, 5, 6. I could say the distance is 6 units. Or what I could look at here is say, okay, well, I could achieve the same thing if I take the one further to the right, 2, and subtract negative 4. Now, I mean, one of the things that we also deal with this is that, well, what if I subtracted the x coordinates in the other way? And say I took a negative 4 minus 2, I would have gotten negative 6, which is not really something we report as a distance. A distance, we're just saying, okay, how many units are between them? The negative indicates a direction. If I'm going from negative 4 to negative 2, that means I'm going, from negative 4 to negative 2. That's 6 units to the right. Whereas if I go from 2 to negative 4, that's 6 units to the left. So oftentimes when we do a distance, we'll do an absolute value for that. And of course, the absolute value of negative 6 is 6. And we'll talk more about absolute values as we move through various parts of this course. So a general formula for this is oftentimes to take, the 2x coordinates and subtract them. Now, the assignment of the subscript 2 and 1 is rather arbitrary. It doesn't really matter which one you call x2 and which one you call x1. I mean, so, this could be x1 or x2. I'm going to call it x1 here. This could be x2, but I could also reverse those because of the absolute value. It doesn't really matter. Much the same way in a situation where you have 2 points that are vertically oriented from each other, like this one here. Again, if it's vertically oriented, I could just count. Now the x coordinates are the same, but the y coordinates are what's different. And that's what I would go between, from negative 3 to 1, which, counting whatever you're doing to get there, you can figure out that distance is 4. And I could have done that by doing either negative 3 minus 1 in absolute values, which is the absolute value of negative 4, which equals 4. I could have done the absolute value of 1 minus negative 3, And of course, subtracting a negative, same thing as adding. So this is 1 plus 3, which is the absolute value of 4. Make sure they look like bigger, and that's 4. So the general formula when I have two things vertically oriented is to subtract the two y coordinates and take a look at their absolute values. So not a big deal there. So vertical lines and horizontal lines, or vertical distances and horizontal distances, are pretty easy to come up with. The third case, and the most frequent case you're going to deal with, is what if they're diagonally oriented? And I have a slanted line. What do I do with that? Well, what I can do with that is realize, okay, well, if I kind of find a horizontal component for the distance, I could turn this slanted line, this kind of gets into concept of slope, which we'll talk about momentarily as well, and kind of break this up into two components where, this distance here is x2 minus x1, and this distance here is y2 minus y1. What I set up here is, I could bring this up into a horizontal and vertical distance, and recognizing that this is a right triangle, and remembering some of your high school level math again, I could find this distance here using the Pythagorean Theorem. And that Pythagorean Theorem would say I would take this distance here, add this distance here, both these being squared, and that would equal, I'm going to call this distance d squared. And to solve for d, I would square root both sides. Now, one of the things we talk about later is that when we put a square root into a problem to solve the equation, we really should put a plus or minus sign there. But again, remember, distances are always reported as positive. So in this instance here, I'm not going to put a plus or minus symbol in because distances are never reported as negative. Now, if I'm looking for a movement, that's a different case. And this is what we know as the distance formula. And this would work with horizontal and vertical line or vertical distances as well, but it's mostly geared towards finding the distance between any 2 points on the graph, and it's more geared towards slanted lines, much like this one. And most of the ones you're going to deal with are going to be slanted lines. So what I would do in the case of, say, for instance, example 3, is I would define, again, the assignment of which are the x1s and which one's your x2s and so forth is rather arbitrary, because in the end, even for the distance formula, you don't have the absolute values involved, but you are squaring them. And so if you square a positive or a negative, it ends up becoming a positive value anyway. So which x values I'm calling x1 and x2 doesn't matter. Which ones I'm calling y1 and y2 doesn't matter. Just make sure that you are calling the x's x's and the y's y's. And for an ordered pair, the first coordinates are the x's, the second coordinates are the y's. Setting this up, and again, if I could reverse the x1 and x2s and the y1s and y2s, as far as the coordinates go. To figure out the distance, I'm going to set up the formula. Negative 3 minus 4 is a negative 7. Squared is negative 7. I get 49. And again, some of this could be aided with you on the calculator, which is fine too. 7 minus 4 is 3. Squared is 9. And I get the square root of 58. It's an irrational number. 58 is not a perfect square. There are no perfect squares that would divide out of 58. And so, the best I could possibly do to go any further, if I wanted to leave it exact, I'd say the square root of 58 If I want to get an idea what that is, I could approximate it just by doing the square root of 58 on my calculator. And the square root of 58 is approximately 7.62. So these are about 7.62 units apart. Now, distances can be used along with other things and other concepts as well. So let's have a look at example 4, which is a question that is often posed, or similar questions are posed to it in textbooks a lot. So for this one here, we want to show that the following are vertices of a right triangle. So, well, how would we possibly do that? I could graph it, and certainly a graph is useful for this as you try to find the correct distances, because it's the distances I'm looking for. And basically, if these are the vertices of the right triangle, then the sides that run between these various points would, as a result, be following the Pythagorean theorem. So the first thing I'm going to do is I'm going to sketch a graph of this. And so again, I'm going to speed up the video so I can show the drawing. And so that's what my triangle more or less looks like. It's a quick sketch, but I can kind of see that, this more than likely was where the right angle is going to be. So I'm going to call this side A, I'm going to call this side B, and this side C. And I want to be able to show that A squared plus B squared equals C squared. And I could define what A, B, and C are. A is the point that goes from 1, 1 to 3, 4. B is the length that goes from 1, 1 to 4, negative 1. And C is the segment that goes from 3, 4 to 4, negative 1. And so I want to find these various distances. And again, I'm going to use the distance formula for this. So, you have your x's and y's. So A, if I set the distance formula, which equals the square root, 1 minus 3 is negative 2, squared is 4. 1 minus 4 is negative 3, squared is 9. And that equals the square root of 13. And instead of calling that D, I really should just call it A, because that's the distance A. So the distance A is the square root of 13. B, same thing. 1 minus 4 is negative 3, squared is 9. 1 minus negative 1 is 2, squared is 4. So I get another square root of 13. C, 3 minus 4 is negative 1, squared is 1. 4 minus negative 1 is 5, squared is 25. So this equals the square root of 26. And so now I get back up to the original problem here now. Is this true? So if I take the square root of 13, which is what A was, and square it, and take the square root of 13, which was what B also was, and square that, does that equal C squared, which is the square root of C being the square root of 26 squared? These are pretty easy because if I square square roots, all that happens is the square root and the square cancel. So I have 13 plus 13 on this side. Does that equal 26? Well, yeah, it does. So since the three lengths that make up the triangle obey the Pythagorean theorem, that is a right triangle. And I was able to do that using the distance formula. So an involved problem, but nothing in particular that was too difficult. The distance formula is just basically knowing what the formula is and making sure that you plug it in correctly. Then the rest of it came from just being able to calculate the Pythagorean theorem out. As we move into example 5, we're asked for something different here. And make sure that you do know the difference between finding the distance between 2 points and finding the midpoint between 2 points. Just as a really quick graph of what's going on here. And what I'm looking for is to figure out what point is exactly halfway, or the midpoint, between these two. Now, I didn't draw a really accurate graph, so that could be somewhat tough to do with this one. But even you would find in many cases it would be tough to do it even if you had this drawn on a nice coordinate system and things of that nature, because that point is not necessarily guaranteed to cross at your grid marks, and it also would depend upon how you had it scaled as well, whether or not it would. So that you would be doing some speculation and guessing. Whereas the midpoint formula is really not very difficult. The midpoint formula is basically telling you, again, I'm going to have points defined. These are a pair of x and y coordinates. This is another pair of x and y coordinates. The subscript of 2's, again, doesn't really matter so much, even in this formula, because essentially what you're going to be doing is taking the average of your two x coordinates, so add them together, divide by 2, and I'm going to do the same thing with the y coordinates. And that's it. It's a very simple formula. Even the distance formula wasn't extremely difficult, just had more things going on with it. This one is more straightforward in the fact that all you're doing is adding a couple things together, then dividing by 2. So for this case here, for this situation here, the midpoint on the line segment connecting these 2 points would be -5 plus 4 is -1. -1 divided by 2 is a -1/2. So unless you're scaling your graph by halves, which most people usually don't, this would be something you're guessing at. 2 plus -6 is -4. -4 divided by 2 is -2. So that would be the precise coordinates for this midpoint. Now, for whatever reason, your textbook chooses to go into the equation of a circle in this particular unit. And in actuality, you really don't see circles a whole lot in the rest of this course. If you look further in the textbook, you do see that there is a chapter on conic sections, which goes into circles again as well. However, we don't cover that in this course. So it's still rather easy because it has a very set structure. The formula for the equation of a circle's equation is generally this form here, where I have x minus h squared plus y minus k squared equals r squared, where the h, the k, and r, and therefore r squared, are constants. So the x minus, the y minus, the parentheses, the squares, the plus sign on the left-hand side are all part of the structure of the formula. And it basically tells us that the center, if I have it in that kind of format, is at h comma k. Do notice how these have minus signs up here, but the coordinates do not. And the radius of the circle is r. How do we use this formula to do this? One of the issues we have with this particular example here is that this has a plus there where it should have a minus. This one's fine. I have x minus, and I do have a number. Great. That should be my h value. That should help me figure out where the center is. The fact that I have the y plus 1 is concerning, but it's something I could easily resolve because remember, an addition is the same thing as subtracting a negative. And so if I think of y plus 1 squared as y minus negative 1 squared, if I get a square up there, I'm fine. And of course, 9 is the same thing as 3 squared. Now I can clearly see better what my h, k, and r are. This circle is going to have a center at 4. It's the number following the minus sign, negative 1. This number following the negative sign. And the radius equals 3. So, I'm going to plot 4, negative 1, which would be right here. And the radius, I'm just going to move right 3 units from that point. Starting at the center again, I'm going to move up 3 units. Starting at that center point again, I'm going to move left 3 units. And from that center point, I'm going to move down 3 units. And I'm just going to connect it with as best a circle as I can. I don't expect perfection with your circles, just don't get too lazy with them. I've seen students do this, and it's more of a pet peeve of mine. Don't do this. Do not draw a diamond. Don't just connect the dots and say, okay, that's my circle. That's not a circle, that's a diamond. Try to make it at least look rounded, so that if it looks too much unlike a circle, I will take a point off of that because you're drawing me a diamond, not a circle. Now, do the same thing on calculator, which is something that you are also shown, just to verify how to do this. There is a command on TI 83 and 84 calculators. Let me go there. And just to make sure there's nothing in the way of it, I'm just going to clear off the graph. If you go to second in the program button, that's going to be the draw menu. It has a lot of different options, but you can see choice number 9 is circle. And all I need to do here is put in the h, the k, and the r values in that order. So in this case here, my h value was 4, comma. My y value was negative 1, comma. And my r value was 3. And I could make it draw a circle. I mean, the thing is, you still have to be able to interpret the equation correctly to do it. So you're not really saving yourself a whole lot of steps. It's just checking to make sure you are plotting things in the right points. So I hit enter here. Now this is on if I zoom to a standard, which is like everything negative 10, 10, it looks very elliptical. Let me go back to anytime you change this. This particular function, it makes it go away. It looks like very elliptical, but if I do a zoom and do a zoom square, and again I'm going to have to quit and then redo this. I'm in the second and enter to pull back the exact last thing I typed. As you can see, it looks more like a circle in that instance as well. So again, I mean, it doesn't really save anything. It's something useful your calculator can show you to see if you're on the right track. But you still have to know how to interpret the parts of the equation of a circle anyway. The last thing you're asked to do is then to, given a circle, to write the equations of them. So let's have a look at that. So here is the graph of two different circles. And again, you're asked to find the equation of it. Now, as you can see here, I mean, the first thing you have to do is locate where the center is. And I can see, the center should be the midpoint between, these horizontal points here and these vertical points here. Now, they're not going to be super difficult because of the fact that, these are horizontally and vertically oriented from each other. You can see really quickly that 0, 0 is the center. I'm going to mark that as C. And I can see that, from that the radius is 4. So I can write that as x minus 0 squared plus y minus 0 squared equals 4 squared, which would be 16. That having the x minus 0 and y minus 0 in parentheses is kind of, over the top. I mean, because x minus 0 is just x, y minus 0 is just y. So anytime you see just the x or the y by itself being squared and not in a quantity being squared in the equation of a circle, simply means that that particular coordinate for the center is going to be 0. That's all it means. For B, again, it doesn't take very long to see that here is my center, and my center, which I'm going to call C again, it looks like it's at -2, -1, and it looks like the radius is 2. So again, following the structure, I'm going to write x minus, because that's part of the structure, -2 squared plus y minus -1 squared equals the radius 2 squared, which of course is 4. And the minus and negative, as we've seen before, as we undid it before, but I can further simplify that and just say that's x plus 2 squared plus y plus 1 squared equals 4. And so there are your equations for these two. And that brings me to the last example for 1.1. And now I'm going to go into section 1.2, dealing with functions and graphs. One of the things that they definitely want you to have in mind as we proceed is the concept of a relation versus a function. A relation is a correspondence between two sets. That's all it is. So oftentimes, it's the correspondence between two variables. Primarily we use x and y. But it could be any two sets of things. It could be like, and it could be represented in many different ways. A figure, a table, ordered pairs, just various data. I mean, there's different ways to represent relations. Now, a function is a relation where each element of the domain corresponds to exactly one element of the range, which means, as far as we go for, a lot of our formulas, each x value produces exactly one y value. Each input only produces one output. I could have two input values produce the same output, but I should not have one input value generating two different output values. So let's go into, see how we could define what functions are, based off of different ways they could be represented. For this first one, these are both given more of a diagram, and when I have, the arrows are always pointing from the input to the output. And so we want to know, are these functions or not? For A, Sean produces bowling only. So Sean's favorite activity is bowling. Dave's favorite activity is golf. Melissa's favorite is tennis, and so is Joanne's. But since Melissa only generates tennis and Joanne only generates tennis, this is a function, because each input, each name, only is associated with one favorite activity. On the other hand, when I look at the next list, x, the input of x produces an output of 10. For y, the input of y produces an output of 20 and 30. Because of this here, this is not a function, because I have an input y producing two possible outputs, and that's not what a function does. Now, Another way that we can represent relations is by using sets of ordered pairs. So again, what I'm looking for here, sets of ordered pairs are putting together two inputs and outputs together. And so what I have here are a bunch of x's and y's being shown to us here. You know, x, y, x, y, x, y, x, y. I want to see if this is a function. Well, 3 is associated with 4. There's no more 3's in the x-coordinate position, so that one seems to be fine. X-coordinate negative 2 produces 1 here, but the issue is it also produces a 3 here. And because of that, this is not a function. On the other hand, when I look at the next one, and one of the easiest ways to determine if I have ordered pairs, if I have a function or not, I can see that each x-coordinate is only written once. If that's the case, I don't really have to check to see if each one's paired with a unique its own y coordinate. If it was repeated, I have to see if it's associated with the same y coordinate. But because of this, each input, each x, is associated with only one y. This is a function. And ordered pairs could also be represented with tables, and tables could therefore also represent relations and functions. So let's have a look at those. So I have these, and again, I'm representing two situations that students often get confused. Here, I have x being 3 and only 3. But x being 3 produces a 1, it produces a 2, produces a 3. So basically, the input value of 3 is producing 5 different outputs. This is not a function. However, on the other hand, when I look at the next one, the x is again only appearing once. I mean, they're all producing the same y value. So it could be like me having x here, y here, and I have 1, 2, 3, 4, 5. I just have 3 here, and they're all going to 3. That's fine because the x value of 1 only produces 3. The x value of 2 only produces 3. The x value of 3 only produces 3. They can all produce the same output. However, as long as that's the only output each one represents, so this would be a function. So if I'm looking at a table, kind of going back to the first one, and and I see this, and I see 1, 2, 3, 4, 5. When I see this diagram, and I see that there's more than one arrow coming from a particular input, that's a sign that it's not a function. Whereas if I see a bunch of arrows come towards an output value, that's fine. As long as I don't have more than one arrow coming from any input value, that makes it a function. So we have a somewhat idea what a function is. Let's talk about the graphs of functions when we actually look at graphs. One of the things when we're looking at graphs is we use a vertical line test to determine whether or not a graph we're looking at is a function or not. Basically, the vertical line test is stating that if I'm able to pass a vertical line through a graph, as long as that vertical line only touches the graph once, it is a function. If it touches more than once, it's not. Which means that it essentially is the same definition because if I have a vertical line, if I have like 2 points that share, a vertical line passes through them, that means I would have say x here was 3. Here, this number here is clearly different than this number here because one's positive and one's negative. That means I would have the input value of 3 producing at least 2 different output values. So that would mean that it's not a function in that kind of case. So that's why we use that vertical line test. Now, here they're asking you to determine if y is a function of x. using the following. So basically, you have to know what these formulas look like. Now you can graph them, but some of these things won't graph very well on your calculator. So this one here we haven't talked about yet. It's a quadratic. We're gonna get more into that. We talked about circles, so let's have a look at the circle instance. So I'm going to look at these, and look at the circle instance first. And that's pretty straightforward because if you graph that circle, from what we learned in the previous lesson, this is a circle that has a center at 0, 0 and has a radius of 2. So in the end, it would look something like this. Well, as you can see, it fails the vertical line test. So this is not a function. And some of these other ones, it'd be kind of hard to graph them. Because, for you to graph them, you'd have to have them solve for y. A is already solved for y, whereas C and D are not. How you would go about solving them for y would indicate whether or not they're functions or not, because to get a total graph on your calculator only graphs situations like A, where I have y alone on one side of the equation, all the other stuff on the other side. So, A, I can graph that, and if I go to my calculator and graph that, pulling up my calculator here, and I graph y equals, the y equals is already there, 3x squared minus 4, and I graph that, I can see that, this is what we would call a parabola, and I'll do a quick sketch of it on here. So it looks something along the lines of this. And as you can see, if I pass any vertical line through this, it's only touching this parabola once. So this would be a function. And I've shown that graphically. Now these other two I'd have a little bit more problems doing graphically. So let's have a look at them and see what I would need to do to make them be done graphically. For C, I'd have to solve this equation for y. So it gets into some equation solving things. I'll subtract x from both sides, which would give me y squared equaling 9 minus x. And now I have to get rid of that square. Now, I had brought this up before in 1-1. When we take a square root, we're supposed to put a plus or minus symbol on both sides, on the side that we're, the non-variable side, where y here is being treated as the variable because I'm trying to isolate that. So if I'm going to do this correctly, there should be a plus or minus symbol here, which would give me a final equation of y equals plus or minus the square root of 9 minus x. So with this in mind, is this a function? Well, the answer to that is no. And I'm going to show this graphically. Anytime that you have to put this symbol in the process of being able to get it to a point where you could graph it in this notation and put it on your calculator, this is going to make it not a function. And I can show you why, because here, well, first of all, for me to do this on my calculator, I had to enter it in two different parts. Clear that. I had to first do the square root of 9 minus x. And then I had to do negative square root of 9 minus x. Make sure on this calculator you know the difference between the minus sign, which does subtraction, and the negative symbol, which is for an indicated negative value. And if I graph this now, now it's showing it in two different colors because I had to draw it in two separate graphs, but essentially it's a sideways parabola. So the graph looks something like this, but as we can see here, it fails the vertical line test. So that plus or minus symbol, I mean, that's going to create situations where a single x value, so say like I chose x to be 0. Well, if x was 0, the square root, that would become the square root of 9, which is 3. Y would be plus or minus 3. I would have two different y values for a single x value. Whereas with the last one, in order to get y alone, I would just subtract x cubed from both sides. And my final formula would be y equals negative x cubed minus 4x. As you can see, I had no reason to put a plus or minus symbol in there. And from that algebra alone, that would tell me that that's a function. I was able to isolate the y without having that plus or minus symbol being required. And I can again show this and prove this by using the graphing calculator and show if I put in the formula I was able to come up with, the graph essentially is doing this. And essentially, you know, if I draw any vertical line through this, it's only going to touch that graph once. So, you know, although they want you to do this graphically, in order to do it graphically, some algebra had to be done, and that algebra, you know, would have to include the plus or minus symbol. I could have done the circle in a very similar way, because if I solved, for instance, this for y, and again, this part right here is going to tell me it's not a function just algebraically. So, you know, they say do it graphically, but the fact is you could tell if it's going to be a function or not in the process of making it something you could put in for a graph. Because some of these things we haven't talked about yet, and we're not able to do so yet. So you'd have to put it into a y equals format, and in the case of doing that, you'd already have the information you need to know whether or not it's going to be a function or not. So let's talk about what function notation looks like. As function notation, once I establish that something is a function, I can rewrite it in function notation, which is kind of a shorthand. So function notation, basically, when I have these formulas that were above, I had y isolated, but now I'm basically assuming that y equals some function of x. So you're going to see f of x in the place of where y was. That's really the only difference. And what it is some of these things are shorthand because it says, okay, if I have f of x being defined as this function, so the function f of x basically is telling me that I'm going to take an x value, square it, multiply it by 3, and then add 2, and that's following my order of operations. Well, then if I replace x with anything else, that's what I would do to whatever that is. So for instance, if I wanted to do f of negative 2, that's going to equal 3 times negative 2 squared plus 2. Negative 2 squared is 4. 3 times 4 is 12. Plus 2 is 14. So f of negative 2 is 14. F of 3 would not be much different. Again, the only thing that's different is I'm going to go to the function f of x, and I'm going to replace x with the 3. And usually we use the parentheses for this case, even though there's nothing going on inside them except the number 3, to indicate that I did do a substitution there. Something was replaced with this 3. I then follow my order of operations. Nothing to do inside the parentheses except the 3, so I'm going to take 3 now and square that and get 9, multiply that by 3 and get 27, and 27 plus 2 is 29. Now, for some reason, when you replace X with some other letter, some people lose their mind and think, okay, well, I have no idea how to do this. It's really not that difficult. All you're doing is replacing the X with an R. So, in many cases, these could be very straightforward. This is going to be 3. I'm replacing the X with an R squared plus 2. And the only thing I could do beyond this to simplify is really get rid of the parentheses, because I really don't need them here because I just did them to show the substitution. Without knowing what R is, I had to square it first before I could multiply it by 3 and then add the 2. I don't know what R is. So 3R squared plus 2 is as far as I can go with that. So that's all there is in those kind of instances. So let's have a look at B. So one of the first things you have to kind of get in mind here is that if I'm given a function defined by a formula in function notation, now g of x is replacing the y, this is function g. And the reason why that would sometimes be done with a different letter is if I have more than one function going on, I might want to know which one's which, so I'm going to name them differently. So I say, okay, if I say g of 3, I'm going to go to the function g and plug in a 3 for x, and not go to the function f and plug in a 3 for x. For the first one, since I still have a variable involved in the problem, the final answer is going to have a variable in it. It should be an expression. Whereas for 2 and 3, I just have a number in there. So I would expect a numeric answer for those because I'm replacing all the x's with numbers. The only time that would not happen is if I had more than one variable in the function, which we're really not going to get to instances where we have one variable defined with several other variables. We'll talk about instances of that really briefly, but we're not going to deal with them in any kind of function notation. So for I, g of 1 minus x would just be me going into this formula up here for g of x and replacing each x, and there's 2 of them, with a 1 minus x. Now again, the first step I do is with the parentheses, just to make sure I know where the x's were and where I'm replacing the 1 minus x. Notice I'm just not putting a 1 minus in some arbitrary spots on this. I'm taking out each x and replacing it with a 1 minus x. Now I could do some simplification. On top, really don't need the parentheses because, the only thing that's going on after the parentheses is the addition of 3. So I have 1 minus x plus 3. The 1 plus 3 would combine, they're like terms. I'm going to have 4 minus x. On the bottom, however, I have a negative sign right here. That has to be distributed. So that's going to become 2 minus 1 minus a negative x, which is plus x. And so what that's going to end up being is 4 minus x over 1 plus x. And that's when it's all simplified. And that's the other thing you have to kind of get used to is that under most circumstances, it's going to be assumed that you are going to simplify. Since sometimes in some elements of tests, especially on the final, you're going to have some multiple choice items. Multiple choice items will always have answers simplified. So you have to take it to a certain point to realize what the final answer is. But getting to the two simpler cases, II and III, for g of 4, pretty straightforward. I'm going to go to each x in the formula and replace it with a 4. Everything else stays. Now I have these extra parentheses which I really don't need. So parentheses 4 plus 3, same thing as 4 plus 3, that's going to be 7. 2 minus 4 is going to be negative 2. So I could say it's a negative 7 halves. I can even put it in decimal form if I want, say it's negative 3.5. We don't use mixed numbers a lot in algebra, so negative 3.5 is the answer. For g of 2, I get a 5 over a 0. I can have zeros in the numerator of a fraction. I cannot have them in the denominator. And we're going to talk about, the fact that, we can't divide something into 0 pieces. We can't take something and divide it until it becomes nothing. So this is not able to be done, and this is undefined. And we'll see how we're going to handle situations like that in more detail as we move through this first chapter. But for the time being, you're just going to say that it is undefined. Determining the domain and range of the functions in interval notation, and we're going to talk about interval notation as we go along with this as well. Interval notation is used a lot in calculus, and remember, this course is under the assumption that you're going to be moving on to calculus eventually, so they want you to become familiar with the notation used in it a lot. So, domains are relatively easy, because we have a domain convention for that, and we look for specific things to tell us whether or not there's any restrictions in my domain. Ranges will usually offer some sort of challenge. I'm not saying they're going to be difficult. The challenge is that you often have to know the type of function you're looking at, and know certain things about it to have an idea about whether or not you're going to have, what any restrictions on your range. They require you to either have a graph of it, which we can, in each one of these cases, we can do a graph, or we have to know something about the function that I can find certain aspects of it to say, okay, well, I know it only goes up this high or only goes down this low, or whatever the case may be. So now some of these we're not going to know all the ins and outs of them, so we'll may have to use the calculator for the time being. However, it gets pretty straightforward after that. So the domain, let's talk about the domains first. So let's focus on domains, and then we'll come back to ranges. Okay. There's a domain convention, and I'm going to repeat it twice verbally. I don't want to write the whole thing down, but basically, the domain of a function, we assume it's all real numbers unless we find something in the equation of it that would tell us that we have to restrict from there. Basically anything that tells us that we would have to say, okay, well, this number has to be excluded because, this number has to be excluded because, so forth and so on. So, that's what we use. We start with the all real numbers, and if I don't see anything that would tell me, hey, I had to restrict this because of one reason or another, then I would be able to, just simply say it's all real numbers in that case. So here, I'm going to start with the domain, saying, well, I would start with all real numbers. But I look at the function more specifically, this thing has a denominator. And from what we talked about in the previous example, we can't have a denominator of 0. 2 minus x cannot equal 0. Because if it would equal 0, well then, this fraction, this function would not exist. I would have an undefined value there. So I got to think, and it's not a really hard equation to solve here. Well, if x were to equal 2, it would make the bottom 0. So I had to say all real numbers except x cannot equal 2. I am making an exception here. I'm saying that there is a restriction here. So that's how I would say it very much verbally. In interval notation, I would say that x, now this part, this x and this elementary symbol is optional. If you say domain and just put the right things in there, that's fine. I'm going to put a parenthesis. Now in interval notation, parenthesis means that, I approach something but can't equal it. And the reason why I'm doing that here is that I'm going to start at negative infinity, because every other number that possibly exists in the real number system works except 2. So I'm going to say, okay, well then I'm going to approach 2, but 2 is not a part of this domain. Starting at 2 again, but not being part of it, I could go from 2 to infinity, not touching either one of them. On a number line, if I was drawing this domain, I would say it's this. Everything on the number line except 2. And as you can see these two parts on here now. Here's this part here, and then here's this part here. So basically, interval notation is describing what the number line looks like. We're going to get more into how to figure out stuff about this function. There's certain characteristics it has. So, but we'll do that later. For the time being, though, on my calculator, if I want to see what this looks like. Now, on older TI-83 calculators, you may see something different. I'll explain it when I get there. I'm just going to graph this. I'm going to say, okay, the easiest way is using parentheses, x plus 3, my numerator, divided by x parentheses 2 minus x, my denominator. This is what we would call a rational function. We'll talk more about them later. And if I were to graph that, I would have that. And I want to zoom in on this a little bit, so you can see it a little bit better. So you can see what the graph more or less looks like here. As you can see, right here, here's where x is avoiding the 2. This is what we would call a vertical asymptote. We'll talk more about that later. But it also seems to have another horizontal asymptote. And if I look at a table for this, if I get it to actually work, as x keeps going on forever and ever and ever. See at 2 it says error because I can't equal 2. That's an indicator that's a domain restriction. But if I keep getting bigger and bigger and bigger for my x values, you notice it's approaching a very certain value there. As I keep going bigger and bigger and bigger. And in this case here, you find that it's actually getting closer and closer to -1. And if I would go in the opposite direction of negative x's, I'd see the same thing. So basically, the range from what I can see in the graph and the table would be, now again, I could say the y's. But again, this part's optional. As long as I know range, I know you're talking about y's. It's anything but -1. And so in a very similar fashion to what I did above there, I would say everything but -1 in interval notation. Moving on to the next one. Now, when I look at this one here, the domain, I would start with all real numbers. I don't see any x's in denominators, so nothing's going to exclude that. The only other things that would possibly cause exclusions that we've talked about so far are square root symbols. Square roots can only allow certain numbers underneath of them in the real numbers. And in the real numbers, I cannot have any negative values underneath of a square root symbol. Well, I don't see the square root symbol here either. And we'll eventually learn about other functions along the way that would also cause you to have restrictions. But right now, all we've talked about that would have restrictions are having x's in denominators and having x's underneath square root symbols. So there's nothing here that tells me that, that I can't assume all real numbers. So my domain is every number between negative infinity and infinity. That's how I represent all real numbers in interval notation. So if it's a polynomial, which means I just have various powers of x, as long as they're integers, I start getting the fractions that deals with roots again, then I would have an issue. Now, as far as the range goes, we're going to talk about quadratic functions like this. We've seen one already, but for me to know the range, I have to know some specific information and characteristics of quadratics to do that. We haven't gone over those yet. So for the time being, I'd have to use my calculator to help me out with that. A better view. The graph, this is what we call a parabola, and this keeps going up forever. This keeps going up forever, and this will keep getting wider and wider and wider. So again, x could be any number, even though I'm not seeing the graph there. The y, however, looks like it doesn't go below 2. So 2 seems to be the lowest that the y value can be. And therefore, with that graph, I can now say that the range is y values such that, now I'm going to put a bracket at 2 because it looks like I could be 2 to infinity, open parenthesis. Again, the parentheses on the infinity because I can't equal infinity. So, so that would be my range in interval notation. Basically, it's saying all values that are greater than or equal to 2. Now here, the domain. Again, I start with all real numbers. Then I look for possible restrictions. Well, there are certain numbers that do not work underneath of a square root symbol. And basically, negative x plus 4 has to be greater than or equal to 0. Because that makes it 0 or positive. If I have any negative values underneath of that square root symbol, I can't do it. I'm going to add x to both sides for simplicity's sake. I get 4 is greater than or equal to x, which means x is less than or equal to 4. And that's the other part of this. All real numbers such that x is less than or equal to 4. Because if I have anything that's over 4, then I'm going to have a number underneath the square root symbol that's negative, and I can't square root a negative. So, to show this off, I'm now going to say, okay, in interval notation, again, this x and this symbol is not necessary if you put the word domain in front of it. I could go from negative infinity all the way up to 4, including 4, but nothing beyond that. As far as the range goes, I don't really need a graph for this one because we do know some things about a square root symbol. A square root symbol only returns the positive square root. That's why whenever we apply a square root to solving an equation, we got to put a plus or minus symbol in there because we have to remember that, if I square the negative of something as well, I'm going to get the same result. So I know from the square root symbol that, only positive values are coming from that square root symbol. And everything else is underneath that square root symbol. So I'm going to basically say that y, or 0, because 0 could work underneath the square root as well. If I square root 0, I get 0. So y has to be going from 0 to infinity. K of x equals the absolute value of x minus 5. Now, for this one here, my domain, again, is all real numbers. I don't see a square root symbol, so I don't have to worry about, any values of x causing a negative number to appear underneath of a square root symbol. I don't see any x's in denominators, so I don't have to worry about any x values making zeros in denominators. The other thing happening to the x is that it's being absolute valued. And I can absolute value any real number I want to. So the absolute value doesn't cause me to have any restrictions. So all real numbers is the domain. So the range. Now I can graph this, but we can figure this out logically because we know how absolute values work. The absolute value of x has to be greater than or equal to 0. Because that's what absolute values do. If I have a value that's 0, it's going to be 0. If x is positive, well, the absolute value is not going to really do anything. It's just going to, if I say the absolute value of 4, it's 4. If it's negative, it makes it positive. So if I have the absolute value of negative 5, it's going to make it positive 5. So I know this has to be true, which means the absolute value of x minus 5 has to be greater than or equal to negative 5. I'm just subtracting 5 from both sides of this inequality. Just kind of, and this is what k of x is, or what the y value is. So we know that the y has to be greater than or equal to negative 5. So that's my range. And that's just knowing how ranges, how the absolute value function works. So that's the actual range. And for the last one, we have this. Now, I don't see anything in particular that's telling me that, I don't see any x's in denominators. I don't see any x's in underneath square root symbols. So my domain is all real numbers. My range, well, this is a polynomial function, and polynomial functions are something we're going to spend some time on as well, trying to identify certain parts of them. We're not there yet, so I'm going to use the calculator to aid us in looking this over. So, turning this back on. And it looks like it's turning around a couple of times up here. So I'm going to maybe go a little bit higher on my window here and maybe let the y max go up to, let's just say, maybe 20. So as you can see here, the graph seems like it reaches a highest point somewhere up here. And it looks like it's at, and I could usually find the maximums. I'm going to show a quick thing here. I'm going to find the maximum. And I'll find it between, we'll say, -3 and 0. That highest point looks like a y value of 12. So it looks like it goes up to a y value of 12. Actually does so twice. That's the highest it goes. It goes, it bottoms out here, but it goes below this point, at the edges here. And we're going to study more about these as we get more into this unit, into this course. But it looks like the y value has 12 as a maximum. So with that being said, I could say, well, the y value goes from a negative infinity up to 12 and no higher. But I needed a graph in order to establish that. As we move through this course, we're not going to need the calculator as much to identify things. We'll be able to identify certain things along the way based off of using other algebraic techniques to figure them out. But that brings me to the end of section 1-2. If you have any additional questions, please make sure to bring them up in class. Until next time, have a good day.